Yeah. Okay, just want to make sure that you guys can keep going. All right. So, hello, can you guys hear me now? Okay, just want to make sure. Okay, sorry about that. All right, well, what I wanted to say was thank you. Thank you so much because we're doing these, 8-hour live Q&As. That means we hit the mark. We got 10,000 subs. And I just wanted to say thank you for that. I wouldn't be able to have done that. We still have something. Okay, I'm just going to keep going. Just making sure you guys can keep hearing me. But we'll just want to make sure you can. I'm going to keep going, and let's start off with the first question. You can hear. Perfect. Okay, Stacy, thank you. That's strange. I'm glad that it's back on. So I'm going to start off with the first question from Laura asking about redox and electrochemistry, and you have an exam tomorrow, so let's get on that. I wanted to, and a lot of people are asking for these types of questions. Okay, so with that topic, Laura, let me know what you want me to specifically go over, either like balancing redox reactions, which is what I was assuming you probably needed help with, or electrochemistry, like what type, like going over what a galvanic versus electrolytic cell. I can do that as well. So for now, I'm just going to do balancing a redox reaction under basic conditions. I have an example up here ready to go, but let me know what you want specifically. All right, so for now, I'm going to just balance a redox reaction, and we're going to start off with this one. Balancing a redox reaction under basic conditions. And I have an example here. This is aqueous and I2S plus. Okay, there we go. All right. So first things first, whenever we're looking at redox reactions, we want our oxidation numbers. So I'm going to start off with just figuring out what our oxidation numbers are overall. And starting off with this first element, we know that since it has a charge, the oxidation number would then be the charge. So it's a -1. Anything, and in this part, we're going to look at the oxidation numbers that we actually know of. So we know oxygen's oxidation state or number is always -2, or typically -2. And then what I'm going to do is, because this entire compound is charged or has a charge, I'm going to set all the oxidation numbers equal to -2 because we have to figure out what sulfur's oxidation number is. So I'm going to multiply, I'm going to do -2 times the 4, giving us -8. We don't know sulfur's oxidation number, so I'll put an X, and then we'll just solve for X, and that'll tell us what the oxidation number for sulfur is. So that would have been a +6. All right, and then the oxidation number isn't the -8 for oxygen. It's still going to be that -2. I'm going to keep going. Let's see. For anything that's diatomic, meaning like I2, C2, O2, that's going to have an oxidation number of 0. And anything that's just one element in its solid state, or just like one element on its own, has an oxidation number of 0 as well. Now what we want to do is figure out what's being oxidized, what's being reduced, and go from there. So we're going to look at the oxidation numbers, and I'm going to start off with just looking at sulfur. And looking at sulfur, what happened here is it went from a +6 to 0. So that reduced its oxidation state, meaning this is reduction. Okay, anytime we become more negative, that's reduction because we're actually gaining electrons. And then anytime we then become more positive, which is in this case, okay, we went from -1 to 0, that's oxidation. Oxidation is losing electrons, and that's why it becomes more positive since electrons are negative. Then from here, I'm going to build our half reaction. So I'll put oxidation there, I'll put reduction here. And then what I'm doing, what half reactions really are, oh, okay, Laura just stated, yeah, I need help knowing the difference between oxidation and reduction. Perfect, like in the equation. And the perfect. Okay, then I'll relate this back to a voltaic cell in a second, but the half reactions are going to make so much more sense here. So looking at oxidation, I'm only looking at like what elements or what compounds are actually involved in that process. So in this case, oxidation is just going to be the iodide in its aqueous state, and then that's going to go to I2, and it's solid state, and then reduction, we said it was just SO4 2 minus, and this is just a sulfur. Okay. So in this case, I'm actually going to change the question. I'm just going to relate this back to half reactions and how that relates to like a voltaic cell. It's also known as a galvanic cell. Okay, so what I'm going to do next is try to figure out how many electrons are actually being moved or transferring. So going back to oxidation, what I would do is I'd look at, well, on the product side, there's 0, and I would subtract that from the reactant side, so minus -1. That then gives me 0 plus 1, so 1 electron. And where I would place that electron for oxidation, it's always going to go on the products side. And then now for reduction, I'm going to look again and see what changed there, what happened. So here we have 0 and we went to 6. So from 0 minus 6, that gives us 6 electrons. We don't really care that it's negative. Electrons are negatively charged regardless. So that just tells us that 6 electrons have moved or changed. And then from here, I'm going to add 6 electrons on the reactant side. Now, I'm not done just yet because iodide is not balanced. So if I were to put a 2 here, that's actually going to change how many electrons we have, because instead of a -1 oxidation state, it's now going to be a -2 going to 0. So this was really 2 electrons. Okay, so beware of that coefficient in front when you're balancing. And then, so those are my half reactions. Okay, this was reduction. And how that relates to a galvanic or voltaic cell is it's going to tell us which one's the anode and which one's the cathode. So the anode in a galvanic or a voltaic cell is always on the left, and the anode is always going to be oxidation, no matter what, all right? And then, so then in this case, we know oxidation was that iodide, and I would place that here and kind of just tell you, what's happening, what process this is. Here we go. And then now the next one on the right is going to be the cathode, and then that must be reduction. So how I personally remember cathode, like which one's oxidation, which one's reduction, I like to think of it as red cat, okay? That helps me remember that, well, if it's red cat, that means reduction has to go with the cathode, okay? So then that's how you can automatically tell, and then this is, you would write the half reactions below. Sometimes professors want that. The majority of the time they do. Or they would just ask which one, like they would give you a reaction and they would state which one's the cathode, which one's the anode, and so on. Okay, so I hope that makes some more sense. That was voltaic and galvanic cells and how we relate redox reactions with them. I'm going to move on to the next question. I have, let's see, electrolysis. I can go over what an electrolytic cell is, Ria. I know you're just kind of saying electrolysis. Let me know if there's something specific, but I'll go over kind of the difference of what galvanic or voltaic versus electrolytic cells are, because electrolysis has to do with pretty much with batteries. It has to do with here, the differences. It'll make more sense once I draw it out. So let's do this. Okay. So with an electrolytic cell, which is what I'm going to draw here, it's a little bit different. So instead of having the anode on the left and the cathode on the right, it's the opposite now. It's switched around. So now it's going to be the cathode on the left and the anode on the right. Okay. And then the major thing here is that our electrons are no longer moving from anode to cathode, which is what they would do in a galvanic or voltaic cell. However, now it's the opposite. And actually, sorry, they still move anode to cathode. It's just not left to right. It's right to left. Okay, that's what I want you to think of. But still, the electrons will move anode to cathode. Okay, so it's always going to be anode to cathode, just knowing that those are kind of flipped around. So the other thing to note with when you're comparing a galvanic cell versus an electrolytic cell is the overall cell potential. So that actually tells you, will it be spontaneous? Will it be, this type of cell? So for an electrolytic, let me write that, showing you the difference. For an electrolytic cell, our cell potential is going to be negative. Okay. And then another thing is the fact that this is going to be non-spontaneous. Okay, so in an electrolytic cell, we see that, okay, that's going to have a non-spontaneous reaction. It's going to have a cell potential that's negative, and on the left, it's going to be the cathode, then the anode. But then for, let's say, a galvanic, also known as voltaic cell, it's the opposite, where we saw we would have had the anode on the left and the cathode on the right. But once again, our electron flow is still going to go from anode to cathode. And then now our cell potential would have been positive. And of course, it's a spontaneous reaction. So those are the major differences for everybody who's, struggling with galvanic and electrolytic cells. That's something to definitely know. And I've seen those types of questions. The questions I would most likely see on your exam for like this specifically would be either calculating the cell potential and saying what type of cell it is, whether it's galvanic or electrolytic. So definitely know that. Okay, I'm going to move on to the next question from Tuyen. And let's see what we have here. I think it's empirical formulas and molecular formulas. Okay, so we are given the molar mass of serotonin, and that's 176.00 grams per mole. And then as a side note, whenever you're looking at like these types of empirical and molecular formula questions, if they give you the molar mass, that's going to be used to find our molecular formula. So what they gave us already was the molecular formula's molar mass. Okay, that has to be provided, or else you wouldn't be able to continue with the question. Okay, it would have been a trick question or one of those ones that you click not enough or you put not enough information. And let's see what else we have with this. So they also give us combustion of 5.31 grams. A sample was analyzed and it was found to contain 13.3 grams of carbon dioxide and 3.24 grams of H2O, water, and then 15.9%, actually. I'm going to change that percentage to just grams, by the way. So whenever they tell you that, oh, you have this amount of like this percentage of nitrogen or something like that, you can automatically change it to grams. That's totally fine if it's out of 100%. And then we can figure if it is in a second, but I'll show you what to do there. And this would have been N2 since nitrogen has to be, it can't exist just on its own. It has to be diatomic, so N2. Okay, so what I'm going to say is let's start off with trying to figure out carbon, how many grams of carbon we have, how many grams of hydrogen, nitrogen, and oxygen, okay? Because that's what they're telling us is part of our chemical formula. What we're going to do is a little bit of stoichiometry. Let's start off with the 13.3 grams of CO2, and we're going to go from grams of CO2 and make our way to grams of carbon. So I'll start there. So we would find the molar mass of CO2. So let's do that. Finding the molar mass of CO2, carbon is 12.01, oxygen is 16 times that 2 subscript, which gives us 32. And then this entirely would have given us 44.01. So 44.01 grams of CO2 would go on the bottom per 1 mole on top of CO2. Now I'm going to do a mole to mole ratio to give us the moles of just carbon. So everything is 1 to 1. I can tell that because there's only 1 carbon within CO2. So I'll put 1 mole of CO2 and 1 mole of carbon on top. Lastly, all I have to do here is figure out the molar mass of carbon, which we said was 12.01 grams of carbon. That goes on top, and 1 mole of carbon on the bottom. This is going to tell me how many grams of carbon. It's kind of like with these questions, you have to do this step where it's like an additional step where you have to figure out, okay, what's the actual amount of carbon, hydrogen, nitrogen, and then after that, once you finally get there, it's kind of like you're starting the question all over again, and you have to change that to moles. So that's what we're trying to do right now, is figure out the actual grams of each element in this chemical formula. So let's multiply this all out. I'm going to divide this by 44.01, and this is 3.63 grams of carbon. All right, we're going to do this same sort of thing with hydrogen now, and I'm going to use water in this case. So we said that water was 3.2 grams, 3.24 grams of H2O. And then I'm going to make my way to just hydrogen now. All right, so the molar mass, if we were to figure out the molar mass of water, that would have given us 18.02 grams of H2O per every 1 mole of H2O. And then now we want to get to moles of just hydrogen. So do a mole to mole ratio. There's 1 mole of the entire water molecule. And now how many hydrogens do we have? Well, there's 2. So I'll put 2 moles of hydrogens. Next, let's change this to grams. So there's per 1 mole of hydrogen, there's 1.01 grams of hydrogen. Multiply this all out. Let's see what we got. 3.24 times 2 times 1.01 divided by 18.02. This gives us 0.363 grams of hydrogen. All right, and then now I'm going to figure that out. I'm going to keep going and try to figure that out for nitrogen. Okay, so for nitrogen, we're given 15.9 grams of N2, but I just want 1 single nitrogen, so I will multiply by the molar mass, or actually divide by the molar mass of N2. Nitrogen's molar mass is 14.01. Multiply that by 2, and we get 28.02. And then I'll put that on the bottom. That will cancel out the grams of N2, 1 mole on top. And then now, how many moles of N2 do we have? Well, there's 2 of them, so 2 moles of just, I'm going to say nitrogen in this case, and then 1 mole of N2. And lastly, we'll put our grams of N2, which was the 14.01 grams, and 1 mole on the bottom. Okay, and this is of N. All right, so let's see what that was. We're almost there. And then we still have to figure out oxygens. So oxygen will be a little bit different. I'll show you guys in a second. Let's see what this gives us. Okay, it's going to give us the same thing, yeah, which is expected since it's just nitrogen. Okay, so what I'm going to do now, because we had, if you notice, they gave us CO2 and they gave us water. We have 2 different places where oxygen is in, okay, 2 different types of compounds. Now, we cannot just go the route of, okay, let's just try to figure out what oxygen's grams are. Instead, what you have to do, because oxygen is in 2 different places, we actually have to take the sample amount, the 5.31, and subtract it by all the other grams that we found before. And then whatever is left is the amount of oxygen that we have. So that's what we're going to do. All right, and that's always the case whenever an element is found in 2 different places for these types of questions. So we started off with a total of 5.31 grams of our sample, and then I'm going to subtract that from everything. I actually realized the problem. So we said this was only 15.9% of nitrogen, and I realized, hold on, we can't just assume that that was 100% because they actually gave us the gram sample amount. So instead, I would just change that to grams, and I'll do that in 1 second after I just place the values. So this would have been 3.63 grams of carbon, and then I'm going to add these all together, 0.363 grams of hydrogen, and then I'll add how many grams of nitrogen. So going back to the 15.9% of N2. So since that's 15.9%, what I'm going to do is actually change it to a decimal. So, or actually get it out of that percent form by dividing by 100, which is really just moving this decimal place over. So this is 0.159 grams of N2. Okay, and that's what I'm actually going to start off with. So I'll start off, and I'm going to just tweak this a tiny bit, but the setup was still correct. It was just the starting part that was off. There we go. And then everything else is still correct. Let's figure out what we get with this. Redoing that part, times 2 times 0.159 divided by 28.02. Okay, yeah, I figured the same thing as well. Okay, so this would have been 0.159 grams of just N. That's what I'm going to subtract by, and then we'll figure out how much oxygen, how many grams of oxygen are left over. So this is going to tell us how many grams of oxygen. Okay. So let's see what we have. 3.63 plus 0.363 plus 0.159, and I'm going to subtract that from 5.31. What's left is 1.158 grams of oxygen. Okay, so now that we finally got all these values, let's change them all to moles. I'm going to start off with the oxygen since that's what I have. So starting with the oxygen, I'm going to change this back into moles by dividing by the molar mass of oxygen and going from there. So dividing this by 16, we would get 0.07237 moles of oxygen. And I'll do the same thing with all of the others that we found. So we had 0.159 grams of nitrogen. I'll divide that by the molar mass again. Okay, 1 mole. And this, let's see what this part gives us. This gives us 0.11349 moles of nitrogen. And then we were given 3.63 grams of carbon. Let's see what else. I think it was the same sort of thing, just moved over the decimal. Yes, okay. So I'll change both of these. So dividing once again by the molar mass of carbon, 1 mole, we'll see what we get there. 3.63 divided by 12.01. Running out of room. Okay, this is 0.3022. These are longer questions. I know they tend to be extra credit questions. That's normally what I see are challenge problems. Divided by 0.01. Right. Just changing everything out. Okay. 0.359. Finally. Okay. What we're going to do next, after finding the grams and then finding the moles, we're going to divide by the least amount of moles, and that's going to give us our empirical formula. So let's look and see, all right, which one had the least amount of moles? It was the oxygen. So I'm going to divide every single one of these by this value. Okay, so every single one of these is going to get divided, and then we'll see what whole number we can round up to, and if we have to do any special thing. So this would have been 1. Let's see what the other ones would have given us. 0.11349 divided by 0.07237. This would have been roughly 1.5. Okay, the next one, 0.3022 divided by that same exact amount of moles, that would have been 4, and 0.359, and that same value, that would have been 5. Okay, so, and actually this would have been like 5, 7, but still, what I would have to do to figure out the empirical formula, let's say for all of these, I'd have to multiply actually all of these by 2, just because this would have been really 1.5 or 1.6. And then whenever that's the case, by the way, whenever you don't get like a perfect whole number, you would have to multiply the, like if you get like 0.5, you have to multiply all the subscripts by 2. So that's exactly what I'm going to do here, multiply everything by 2. And then I do want to double check one thing, just because then that would have been, I kind of feel like this actually would have rounded up. Let me make sure not to round. That's one thing to be careful about, is when you round like too soon, you could actually get like the wrong answer. So I like really urge you not to do that. So let's just make sure I didn't change this value by rounding off too soon, because I feel like it's not going to be that. That was fine. 6, 8, and this was serotonin. I just want to triple check serotonin's molecular formula to make sure that this is fine. One sec, guys, and we're almost done with this formula. Okay. Let's see. Yeah, we do have to multiply by 2. Okay. So let's keep going. This would have been 2. I'm just multiplying by 2 since this would have been like 0.5-ish. Then this would have made it into a 3, an 8, and a 10. All right. So then if I'm rewriting this all, serotonin, actually this is the empirical formula, this would have been C, H, and then N, and then O. So for oxygen, that would have been 2. For hydrogen, that would have been 10. and then I'm running out of space, and then carbon would have been 8 and nitrogen would have been 3. So 3 and I said 8, I believe. All right, last step for this one is to divide by the molecular formula that was given, or the molecular molar masses formula that was given, and then the empirical molar mass. So what I'm going to do is just quickly figure out what the molar mass of the empirical formula is. So this would have been 12.01 times 8. Hydrogen would have been 1.01 times 10. Nitrogen would have been 14.01 times 3. Oxygen is 2 times that 16. So let's add up that all together. And I highly doubt that they would have this on a, probably an exam question for extra credit, or I wouldn't see it on the final. But unless your professor said that for sure it would be on there, but typically these take way too long. Times 3 plus 32. Okay. So empirical formula would have been this amount, and then molecular was this amount. Let's see what that gives us. Okay. Roughly 1. So that would have been it. Okay, we would have been done there. All right, so the main process with this, or the main concept with this, was just the fact that you had to figure out how to get the original grams. Okay, I think that's like the trickiest part, just knowing how to get the initial grams. Okay, hope that makes more sense. And then Tuyen, I hope that your class is going well. Let me know how it's going, and let me know, when your final is. I'm pretty sure it's really, really soon. But yeah, let me know how it's going. I'm gonna move on to the next question from Abby. And she says, can you help me with titrations? The problem is it takes 83 milliliters of a 0.45 molar solution of NaOH to neutralize 235 milliliters of HCl. What is the concentration of HCl? Okay, so I just wrote everything that we're given. We are finding the concentration, which is also known as the molarity, which is moles divided by liters of specifically HCl. Before I start anything, let's write our balanced equation, because that is necessary for titration questions or acid-base neutralization reactions, which is exactly this. What I'm going to start off with is that HCl, our acid, is going to react with our base of NaOH. And then that's going to give us, remember, an acid plus a base gives us a salt. And then water. Okay, water. So that's exactly what's going to happen here, where NaCl is going to be our salt, and then it will form H2O, or water. Everything is actually balanced here, so that's nice. So that means everything's going to be 1-to-1. From there, what I'm going to do, and the place to start with these questions, is since we're looking for the molarity of HCl, don't start with the milliliters of HCl. Instead, you always want to start with what you're not looking for. Okay, I know it sounds weird, but if you're finding HCl for these titration questions, you're actually going to use the milliliters of NaOH, so the different one. So that's what I'm going to start off with, and the plan for this is to go from milliliters of NaOH, then to liters of NaOH. And then after that, we're going to use the molarity, because remember, we can break apart the molarity to be moles divided by liters, and that's actually going to be used as our conversion factor, okay? So then that's going to get to moles of NaOH. Now that we have the moles of NaOH, we'll be able to get to moles of HCl, and I'm going to stop there. So that's what we're trying to do right now, is we're trying to go from milliliters of NaOH to moles of HCl, because that's going to help us find everything out. We just need the moles right now, since we are given the volume, which we eventually will change to liters, but at the end. Okay, let's start this off. So starting with 83 milliliters of NaOH, I'm going to multiply this and convert it to liters by dividing by 1,000 milliliters, and then to 1 liter. Once again, this is still of NaOH. From there, our NaOH, milliliters and milliliters of NaOH would cancel. We're then going to have our liters, and I'm going to bring back that molarity that was provided. So this would have been 0.45. That number goes with the moles, and it's always per 1 liter. So those are going to cancel now. And what we're going to do is a mole to mole ratio. Since everything was completely balanced in our equation, it's really just 1 to 1. So it's 1 mole of NaOH and 1 mole of HCl. And that's actually where I'm going to stop for that first part. So let's multiply all of those together. 83 divided by 1,000 times 0.45. And this gives us 0.03735 moles of HCl. So that was the first part. Now, the next thing is I'm going to take the milliliters of HCl that was given and convert that to liters. So we'll take 235 milliliters of HCl, divide that by 1,000 milliliters, and that would give us 0.235 liters of HCl. We have the moles, we have the liters. To find molarity, you divide moles by liters. So that's exactly what we're going to do here to find our molarity. Divide those two values, and then that would be it. So 0.03735 moles of HCl, and then 0.23 liters, that's actually a 5, of HCl. Okay. And that's going to give us molarity. So let's see what that gives us. 0.03735 divided by all of this gives us 0. And I'm going to check how many sig figs should we round to. We're only given 2 sig figs. That was our lowest amount, so I'm going to round to 2 sig figs. So this is going to be 0.16 molarity or molar solution of HCl, and that's it. Okay. So that's the main thing for that, Abby. I do have actually multiple questions. This is called solution stoichiometry. So I can see if I can put a previous video that I have. I believe it was titled molarity. It was talking about molarity and solution stoichiometry. So yeah, I'll put that in the chat right now. Make sure to check that out. There's another question in the video for you to try. So that's going to be really helpful. Plus, even in the description box, I believe there is another example. Yes. Yeah, there is. Okay, cool. So once again, I'll put that, and it's called, I believe it's called molarity or solution stoichiometry. And let me move on to the next question. Let's see who's next. Esther's saying, can you go over balancing chemical equations? It confuses me all the time. Thank you. Sure. So let me pick something to balance. Let's see what we have. Let me find something real quick, just an example as you guys start to add more questions here. Balancing. Okay, there we go. Sure. So let's start off with maybe something like this. Okay. So let's just start off with trying to balance this out. Now, what I personally like to do, let me finish this up. There we go. Okay, so what I personally like to do when I'm balancing is to separate all of the elements like apart from each other. So I'm going to put each element on one side, so on the reactant side, the left, or the product side, the right. So I'll see that there's Ba or barium, and then chlorine, Na, and then now for any sort of polyatomic ion, we will see that I want to keep those intact. Okay, it's going to be so much easier to just leave them together. So this OH, since it's the same on both sides, and it has to be that case to keep them intact, I'm going to leave that, and I'm not going to separate it to be like oxygen and hydrogen on its own. I'm going to leave them as hydroxide, and then mirror everything else. And then we're going to count, and we're going to see how many of bariums, do we have on either side. So for Ba, there's only 1. For chlorine, there's only 2. And then because of the subscript, and then Na, there's 1. OH, there's only 1. Now I'm going to look at the product side. So for barium, there's 1. Chlorine, only 1. Na, 1. And then OH, there's actually 2 because of those parentheses and that 2 subscript. So, okay, let's start off with just balancing out chlorine. So since this side has 2, and I need 2 on the other side to balance it out, I would place a 2 in front of the entire compound. And what's going to happen is that 2 will actually distribute to each one. Now, a lot of times students think that because we placed a 2 there, what we would do is like add 2 more to what we initially stated, and that would actually be wrong. So beware of that. What you're doing each time is you're going to recount how many of each element you have. And specifically, like if I place that 2 there, I'm going to recount or check what happened when I place that 2 there or put that coefficient in front. Okay, that's what you're doing. You're not like continuing or adding or multiplying to what you previously had before. That was just there to help you know what is left unbalanced. Okay, so then what's going to happen here is that 2 will distribute, and there's 2 NAs, and then that 2 would distribute into chlorine, and now there's 2 chlorines. We didn't touch barium or OH, so those are going to stay the exact same. Next, I want to balance out the NAs or the OHs, either one. So I'll place a 2 in front of this entire compound. Once again, this is going to kind of like distribute, and we'll see that there's actually 2 NAs now and 2 hydroxides, and then nothing else changed with barium or chloride. And right then and there, yep, we're balanced. Okay, so that would be it for that type of question. And then I do have a bunch of videos actually on balancing chemical equations. I actually think I have a playlist on balancing equations. I'm going to put that in the chat, Esther, to help you out. And let's see, I believe how to balance chemical equations. Yeah, it's one of my first playlists. Perfect. So I'll put that, definitely check that out. I also placed one that covers how to balance equations with fractions. So there are certain combustion reactions that require you to use fractions. Don't worry, don't be scared. I explain it all in the video. So I will put that in the chat right now. Okay. So let's see who's next. Okay. Next question is from Gamer. What is the difference between bases and alkalis? Okay. So if we're looking at pretty much the different types, alkalis, if we're looking at alkali metals, that would be the first group on our periodic table, and that kind of tells us the difference already. So alkalis are types of metals. Okay. So that means they are positively charged. That also means that they have different properties of metals. So note that how they behave, it's known as metallic character. How they're going to behave in a sense is they have the possibility of having some sort of conductivity, meaning they can conduct electricity. However, for alkalis, they're not as great as conducting electricity, I would state. That's more of the transitional metals that are going to be better for that. But the main difference between like alkalis, metals would be the fact that they're metals while bases are not. Bases do not consist of metals. Bases actually consist of nonmetals. So that's the major difference. Plus a lot of nonmetals are actually a lot of bases and nonmetals are negatively charged. So it has to do with the properties. It has to do with the elements that are kind of, you know, involved in bases. A type of base would have been something like NaOH, and then specifically that OH is going to tell us that it's a base. Another type of this would have been a weak base would have been something like NH3. And once again, these consist of nonmetals, right? Nitrogen and hydrogen are types of nonmetals. If I were just to look at a base, that would have been hydroxide. That's a really common one. And that would have been like, you know, oxygen we know is a nonmetal. Hydrogen is also a nonmetal. That I would say is the major difference if you were asked that question. Alkalis are metals, positively charged. Bases are nonmetals, negatively charged. Okay. And cool. And then real quick, Gamer, I see that you had another quick question that I could answer real quick. And knowing, hold on. Can I know ether, it's aqueous or solid? Oh, either is aqueous or solid. Got it. Okay. So understanding which one's aqueous or solid, that does have to do with the solubility table. So I can place in I have a video on how to use the solubility table, and you could actually download my free solubility table as well. I believe it's titled or called How to Use the Solubility Table or Solubility Rules. That's going to tell you whether it's aqueous or solid, and it goes over every single type that you will possibly see. Okay, so that's going to be really beneficial. I'll put that in the chat right now. All right, and let's move on to the next question. And then guys, if you, of course, need help with solubility, solubility rules, and all of that, definitely check out the video that I'm just going to put. And you can, if you haven't yet downloaded the solubility table, you can find that on the video that I'm going to place. You could also find helpful formulas of all the different formulas that you will need for this semester of chemistry. Okay, I know that there's so many different formulas, and I always hated flipping through my book or flipping through my notes, not finding the one formula that I wanted. So I put them all together in this formula sheet. So where you can find that formula sheet is actually in the description of this video. So if you go to the description box of this video, you'll already find that you can find that that formula sheet for you. It's called Chemistry Survival Guide. Okay, so that's completely free. Download that. All right, let's see the next question from Angie. Could you please show how to draw that? And then on a side note, do you know why 2,4-dimethylhexane has a methyl group in its name and 3,5-dipropyldecane doesn't? Thanks. Dipropyl. Oh, okay. And then Angie just stated, sorry, I forgot to mention to draw that as a line structure. Yeah. So skeletal, I know what you're talking about. No problem. Here, let's go over how to draw this. So for those of you seeing this right now, this is a bit of OChem. If you're continuing with chemistry or going to be a chemistry major, something to do, or even something in like health professions, you will possibly see this. So this is good little glimpse of it. So looking at something like this, all right, so we have CH3, CH2, and oxygen on either side, and I have a CO at the end. Okay, so what I'm going to do for this is when I'm drawing this, the fact that they're telling me that there's two of them, right, then I can tell, well, I know carbon and carbon, and there's an oxygen attached. So what I'm going to do is, as a line structure, here, I'll show you where everything is going. So carbon is represented in OChem as just like a single point. And I'm kind of like showing that, like this is how it would look like, but this is one carbon, this is another carbon, okay? And then that's attached to oxygen. Now with OChem, you don't really see the hydrogens. They're invisible. They're kind of just there. And how you would kind of know that is the fact that, you know, this goes back to this goes back to, what was it? The octet rule. The octet rule where carbon wants to have 8 valence electrons, or really 4 bonds. So that's why they're invisible, that we just know that they're there. So that's the first part of this. That's kind of like what's in parentheses. And then we're going to have 2 of those attached. So what I'm going to do now is, because we stated that there was a carbon here, right? There had to have been a carbon here, and I'll just label that once again as a line. And then plus, I'm also going to mirror that on the opposite side. So that means that this is also going to have oxygen and have it again. Here, let me make this better. There we go. So this is going to be representing one of those groups, okay? So one of these. And then this second part is representing the second half. So that's kind of what you would do. You're going to have 2 different types of those groups on either side of this specific carbon. Now I still have to attach that carbon to oxygen. And what's going to happen is that that's going to actually have a double bond. That's what we would do whenever it's like CO, that's your hint that there's not going to be a hydrogen whatsoever. Instead, it's just going to be carbon double bonded to oxygen. So that's what this would overall look like. Now, to answer the other question, how do you know, or do you know why 2,4-dimethylhexane has a methyl group in the name, while dipropyldecane doesn't? So I would have to draw it. So I'm going to draw those real quick, and I'll show you how I can draw just looking at it. So this was 2,4-dimethyl hexane. And then I'll compare that to 3,5-dipropyl. Okay, dipropyl decane. Okay, so let's start off with the first one. The fact that it's hexane, I know hex means that there are 6 carbons in the carbon chain. So a little trick for you too, when you're trying to draw these out, what you would do is you actually like mentally think, oh, I'm only going to draw 5. Like here, I'll show you. So like I'm going to think, instead of actually drawing 6, I'm going to think, oh, I'm going to draw 1, 2, 3, 4, 5. And in reality, you actually drew 6. So 1, 2, 3, 4, 5, and 6. Okay, when I found that trick, my life was changed in OChem and it made my life a little bit easier. So, because I was always drawing too many beforehand. So, okay, there's that. Now, next, what I'm going to do is state the location of that methyl group. They tell us that it's at 2 and 4. So I'll label this 1, 2, 3, 4, 5, and 6. At 2, we have to show that methyl group, which is just a line, and then 4, another methyl group, which is just a line. All right, so we'll see what the other one looks like. Now, decane is actually going to be 10. So I'm going to draw this out. 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's my trick. So that actually would have given us 10. And then next, this is telling us 3 and 5 is propyl. So propyl has 3 different carbons. So let me label this out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And propyl we said was 3 carbons. So at 3, I'm going to do 1, 2, and 3. 1, 2, yeah, that's fine, because this is the 1, 2, and 3. And then next, I'll do that also at 5, same thing. Okay. So let me see real quick why that would have been the case. I do believe it's in the structure. That's the longest chain. Why it isn't methyl. Has a methyl group in it, and then 3 that doesn't. I think I kind of just answered the question there. But 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, I did. Okay, so all that really was the reasoning for this is the fact, or the type of substituent it's called. So what substituents are, by the way, I like to think of it as like the carbon chain is the body, and then these substituents are like the little limbs or arms that are sticking out. So these would be our substituents that are known as propyl. And then here, methyl would have just been, at 2 and 4 would have just been here. Main difference with this, methyl just means that there's 1 carbon, okay? 1 carbon, while propyl means that there's actually 3 carbons. So that's the reason behind it. It's just how they're all grouped together. It's how they're written out. So in naming, you would actually look for the longest carbon chain first, and you would then number it according to highest priority. Actually, you would number it where the substituents would have the least number, and then from there you would actually list the substituents. So that was the main thing, just knowing what the difference between a methyl and propyl group are. Methyl's 1 carbon, propyl is 3. Okay, so let's see another question. I think from Jazzy saying, can you do solubility curves? Sure. Let me see if I can pull up something on solubility curves. Let me know if there's something specifically about solubility curves that doesn't make sense. I'm assuming probably just how to read them. And let me find one real quick to give you an example. But let's see. Let me see what I can find. Just looking for an example. But Jazzy, if you know what doesn't make sense of solubility curves, let me know. What I'm going to do is just draw a generic solubility curve and tell you how to read it. I believe that's the question. but here. So what a solubility curve is going to look like is that on the x-axis, it's going to be the temperature, let's say measured in Celsius, and then I would have stated, let's say, the grams of solute divided by grams of water. Okay, let's just state that. So something like that would have been on the y-axis, and then you would see a bunch of like lines or curves, and I'm just going to start off with drawing one of the lines. So it would have looked like this, and then let's state that this is at, I'm going to say 5, and let's see, yeah, let's say that's at 5, this is 70, and then this is like 45. Okay, so let's say if the question asked at 45 degrees Celsius, how many grams of water will be needed to create a saturated solution, or even kind of just looking at it as at 45 degrees Celsius, is this soluble, or is this gonna work? Okay, so kind of like looking at what this is even saying, how you would read this graph is they would tell you a specific temperature and you would go to it and you'd look, okay, will that be soluble? And they'll tell you that, oh, maybe it's going to be soluble at this percent by mass. Okay, that's something that we can look at. So if it were percent by mass or mass percent, that formula would have been grams of our solute divided by the grams of our solution times 100. So let's say if, let's see what else I can state with that. Let's say if they gave you 350 grams of KNO3, and let's state that this is KNO3. Okay. And we're asked to find, will this be soluble in this solution? Okay. So if that's the amount that we have and how we're going to pretty much read this table and see what's going to actually make this soluble, or what is going to be the mass percent of solubility. How you would read this is basically like this. You'd state that at 45 degrees Celsius, this exactly goes to, or it hits the point of 70. Okay. And then from there, you can state that, oh, since this is 70 grams of our solute, that would be over 100 grams of our water or our solution. Okay, so that would have, let's say if this is our actual solution. So that actually means that it's 70% of our solute that is in our solution. Okay, that's the mass percent of our solution. So that's something that you can possibly think of. I don't know if that was your question. Let me know, but that's how you would look at a solubility curve. Okay, I'm going to move on to Kieran Loney, write a balanced equation with state symbols to illustrate how NaNO3 can be prepared in the lab. Explain why NaNO3 can be prepared utilizing the same method to prepare CaCO3. What do you mean by prepared in the lab? Let me see if there's anything else with that. But write a balanced chemical equation with state symbols to illustrate how NaNO3 can be prepared in the lab. Oh, I see. I believe you're stating like, how can we form that? Like, that's our product, and then what would our reactants be or look like? Let me know if there's more to that question, but let's see if I can find an example or do something with that. Here. Because I feel like that's more of a lab question, but let me see what I can pull up and find with that. One sec, guys. I'm thinking, okay. I have an idea with that. This is what I would think you would do using the same method to prepare calcium. Yeah, carbonate. Okay, yeah. Then that is right. So what I'm thinking here is what this question's asking is how can we actually use, like, let's say an acid or a base or salt or something to combine and then form that product of sodium nitrate. So what we could have used was some sort of acid that actually contains nitrate. So I would said nitric acid. So I would use HNO3, that's aqueous. And then I would have combined that with, let's say, I need something that has Na. So I could have used some sort of salt like NaCO3. Let me balance this. This would have been a 2 here. So I could have combined those two together, and then I can look at solubility and see what's actually going to react and form. So if that was a salt, let me just double check my solubility table and go from there. But carbonate is typically insoluble with the exception of our first group. So then that makes this aqueous. And then here, NaNO3, NO3 is nitrate. So that's always aqueous. And then this would have formed a product of carbonic acid, so H2CO3. And that actually would have also been aqueous. But that's what possibly could have happened. Let me balance this out now. But that's one way to figure it out, is just knowing, we would start off with some sort of acid like nitric, and then, it's a lab, I figured it was a lab question. Okay. Yeah, so you would have to combine an acid and some sort of salt, which is what I did in the very beginning to then form that. So let me balance this out, and then that would be this question. So once again, I'm going to leave the polyatomic ions together. So NO3, and then we also have Na, and then carbonate. Put those on either side. Okay, and we'll balance this out. So there's only one hydrogen, there's only one nitrate, 2 Nas, and 1 CO3. There's 2 hydrogens, there's 1 NO3, 1 Na, and 1 CO3. Okay, so balancing this out, all I have to do, let's start off with trying to balance out the Nas. So I'll put a 2 in front, and then now think of that as like distributing. So now we actually have 2 Nas and 2 NO3s, nothing else changed here. Now I have to balance out the NO3s and the hydrogen. So I'll put a 2 in front here, and then that's going to now change this to be 2 hydrogens, 2 NO3s, and everything else is now balanced. So this is what I would have seen with that. My hint to this question was just the fact that they said, like, utilizing the same method to prepare calcium carbonate. That's how I figured I would use carbonate to combine with, like, to then form NaNO3. That was my hint in this question. Like, it just helped me figure out what salt to use. Okay, so that would be for that question. Next, let's see what else. Lila says, can you show me how to solve this problem? Let's see what we got. Looks like a limiting reactant question. So if 21.5 grams of aluminum and 34.7 grams of chlorine, or Cl2, react, how many grams of product can be obtained? What is the limiting and excess reactant? And then, okay, so this is a great question for everybody who's studying for finals, for prep, or who pretty much forgot how to do limiting reactant questions, percent yield, excess reactants, and all of that. This is going to be a great question. So let's start this off. And why don't we start this off with just forming our balanced equation? This question stated that we have aluminum, and we're going to add that to Cl2 because any sort of halogen is diatomic, meaning it exists in pairs. And then what's going to happen is those two are just going to combine to form aluminum chloride. Remember that aluminum's charge is 3+ and chlorine has a -1 charge. So this is going to be aluminum and then Cl3. Let's balance this out. So let's keep balancing. So this is just 1 and 2, and then there's 1 aluminum and 3 chlorines. Okay. So what I'm going to do now is, because the chlorines are the only ones that are not balanced, I'm going to try to make this a common number that they share, that they can both go into. So kind of think of it like a common factor sort of thing, where this would have been 6 in this case, right? 3 times 2. So what I'm going to do is I'm going to put a 3 here and a 2 on the other side. And what's going to happen on the reactant side is now we have 6 chlorines. On the product side, this would distribute. There's 2 aluminums and 6 chlorines, so I just have to put a 2 in front of that aluminum, and now we're balanced. Okay, so what I'm going to start off with for any type of limiting reactant question is we want to start off with going from each grams of our reactant to then the grams of our product. And in this case, we only have one product. However, if you were given 2 different products, it doesn't matter which one you choose unless they ask you to find the theoretical yield of a specific product and then use that instead. But other than that, if there was let's say if there was water here somehow, then it doesn't matter what product you decide to go to. But in this case, we only have one product. So that's what we'll start off with. Let's start off with aluminum. Okay, I'm going to start off with aluminum, taking the 21.5 grams of aluminum and making my way to grams of product. So what I'm going to do first is change this to moles by using the molar mass of aluminum. So I'll place the molar mass on the bottom. Let's find the grams of aluminum. That would have been 26.98 grams per every 1 mole of aluminum. Now, since we want to change our compound altogether, instead of aluminum, we actually want the product of aluminum chloride, we'll use a multimole ratio from our balanced equation. And how many moles do we have? There's 2 moles of aluminum per every 2 moles of our product, aluminum chloride. So I'll put 2 moles of aluminum on the bottom so they can cancel, and 2 moles of aluminum chloride on top. Next, we have to change this back to grams to find the grams of our product. Let's find our molar mass, because remember, molar mass allows us to get from grams to moles or moles to grams. So aluminum, we said, has a molar mass of 26.98. Chlorine has a molar mass, I believe, 35.45. Yep. And times 3. And then we'll see what those two are added together. Okay. So I added these two already. This would have been on top. I'm going to place 133.33 grams of aluminum chloride, and then per every 1 mole. Okay. So now let's multiply everything straight across and divide and see what this first part gives us. And then we have to do this all over again for the other reactant. And multiply those two and divide. Let's see what we get. 106.25 grams of aluminum chloride, roughly. So that's just what our first reactant is going to possibly produce. I have to do the exact same thing with the next one, where for Cl2, let's start that off now, okay? So for Cl2, we were given 34.7 grams and of Cl2. Okay, so now let's convert this to moles. What I'm going to do, let's go ahead and multiply by 2 because we have to figure out the molar mass. So multiplying that by 2 would have been 70.9. And then that's grams of Cl2 and 1 mole on top. Same sort of process. Now, instead of aluminum, we want to change Cl2 to aluminum chloride. Let's go back to our multimole ratio or balanced equation. And now we're looking here, and there's 3 moles of Cl2 for every 2 moles of our product, aluminum chloride. So let's go back. So we said 3 moles of Cl2 for every 2 moles of aluminum chloride. And lastly, we'll multiply again by that molar mass that we found before of our product of aluminum chloride. And then we'll figure out which one is the smallest. And we'll do that in a second. Okay. So let's see how much Cl2 will produce. And this is 34.7 times 2 times 133.33. Let's see what we can find. 70.9. Okay. This is 43.5 grams of aluminum chloride. So what I'm going to do now is I'm going to compare and check which reactant produced the least amount. So whatever produces the least amount of product is your limiting reactant. So I'm comparing these two, okay? Comparing these two. So since chlorine produced the least amount, that means chlorine is our limiting reactant. And then pretty much since the other one's left over, then aluminum has to be our excess reactant. Next, since we found our limiting reactant, whatever our limiting reactant produces is then our theoretical yield. Okay, theoretical yield. I've also heard this as it's the, find the maximum amount of grams that you can have or the minimum amount of grams. And it's the same thing as the theoretical yield. Okay, that's just a common question that they ask. So for this first part, they stated how many grams of product can be obtained. That would have been the 43.5. And then what are the limiting and excess reactants? Limiting would have been Cl2, excess is aluminum. Last part of that question is if the percent yield was 54.8%, what is the actual yield? Okay, and actually there's one more part of this question. I remember these questions are like A through D, right? So that actually could be a common exam question or final exam question. So since this was our percent yield already given, remember your percent yield, your percent yield, the formula is actual yield on top divided by theoretical. Okay, theoretical times 100. And how I personally like to remember this, percent yield is where it's at. Okay, that's how you remember it. That's how personally I remembered it on my exams. So that helps in case you forget which one goes where. So percent yield is where it's at. What I'm going to do now is we don't know what the actual yield is. That's what we're solving for. We do, however, have the theoretical yield that we just solved for, and we were given the percent yield. So I'm just going to plug in all the values that we know. So we know this is 54.8. And then I don't know what the actual yield is. I'm going to state that's just X since that's what we're solving for. And then theoretical is 43.5 times 100. First things first, let's divide over that 100 because this is actually still in its percent form and we don't want that. Okay. So dividing that over, this would have been 0.548 is equal to X over 43.5. Last step of this one is 43.5 multiplied both sides to solve for X. So I'll multiply both of those values. X is then going to equal, let's see, so 0.548 times 43.5. This is 23.8, and then that would have been our actual yield, okay? And that would have been grams. Last part of this question is how much excess remains. Okay. What I'm going to do now to figure out the excess, since we really know that our excess reactant is aluminum, we have to figure out how much is left over. So we're going to start off with the actual amount that was produced, which is our theoretical yield, okay? So our theoretical yield tells us how much product will be made. So we stated that our theoretical yield was 43.5 grams of aluminum chloride. And then what I have to do now is I have to figure out how much aluminum was actually used up to make this amount of product. Okay, so what we're finding right now is how much of aluminum was used for the reaction. So then I'm going to multiply this once again by the molar mass, actually divide it by the molar mass, and then on top would have been 1 mole. All right, and then next, we're going to do our mole to mole ratio because we want to get to just aluminum. And we stated before that 2 moles of aluminum chloride, this was going back to the balanced equation. And then lastly, I have to figure out the grams of aluminum. And then the grams of aluminum was 26.98, the molar mass of it, and then per 1 mole of aluminum. Okay, let's multiply this all out and we're almost done. 43.5 times 2 times 26.98 divided by 2 times 133.33. This gives us 8.80 grams of aluminum. This is just how much was used. To figure out how much is actually left over, what you're going to do is subtract the given amount, the given sample, by how much was actually used. So the given amount was 21.5 grams, and I'm going to subtract that by the amount that was actually used. And then finally, this is going to give us how much is left over or how much excess remains. So 21.5 minus 8.80, this gives us 12.7 grams of aluminum that is left over or that remains. Okay, so that's how you do all of that. That's pretty much everything regarding limiting reactants. Guys, if you still need more help with limiting reactants, let me put another video in the chat. It's going to be really helpful. Like I said, if you need any more help with limiting reactants, I will put a video in the chat for limiting reactants. So definitely check that one out. Let me see what the next questions are. And let's see. Okay. We have Min saying, can you please go over how to do stoichiometry at STP? Minha, were you stating? Oh, there it is. Okay, perfect. There's the question. Thank you. Assume that 13.5 grams of solid, let me start writing this down. 13.5 grams of solid aluminum, another aluminum question, react with, and they give us our balanced equation. Perfect. Okay, 6 HCl aqueous 2, all right, yeah, pretty much. Let's see what we're given here. And this is aqueous. Okay. How many moles of aluminum react? All right, let's start there. So first part of this is just figuring out how many moles of, where are we? Aluminum react. There it is. Okay, so all I have to do is convert this going from grams to moles. So taking the grams of aluminum, I want to get this to moles by just using the molar mass. So our molar mass of aluminum using our periodic table is 26.98. And then I would put those on the bottom so they can cancel. And this is going to give us 1 mole of aluminum on top. And that's part A, where that would have just given us the moles of aluminum. So let's divide and see what that gives us. 98. Okay. This gives us 0.50 grams of, I'm going to put one more 0 just because there are 3 sig figs that were involved. Grams, actually not grams, moles. Our grams and grams cancel. This is moles of aluminum. That's part A. So whenever, once again, whenever you're going from grams to moles or even moles to grams, you use the molar mass. Okay, you use the molar mass. That is your conversion factor to allow you to go there. So then now for part B, it's stating how many moles of H2 are produced. All right, so I'm going to take what I just found, the 0.500 moles of aluminum, and then now I'm going to change the element to H2. So now I want to get a mole to mole ratio. So I'll align the units, put the moles of aluminum on the bottom so they can cancel, moles of H2 since that's what we're trying to figure out. And then where I'm going to find these values, these numbers, is the balanced equation. So looking at the balanced equation, there are 2 moles of aluminum per every 3 moles of H2. That's what I'm going to place here. So we have 2 moles per every 3 moles of H2, and then our moles of aluminum cancel, and we're left with moles of H2. So all I have to do is multiply straight across. So multiplying the 0.5 times the 3 and divide by 2, that gives us 0.75 moles of H2. And then for part C, where it asks how many liters of H2 are produced, well, now I'm going to take the previous answer of part B, so the 0.75 moles of H2. And then with STP questions, what they're really trying to get you to memorize and know is that 22.4 liters is equal to 1 mole. Okay, that's exactly what I'm going to use here to convert the moles to liters. So I'll multiply 22.4 liters on top per every 1 mole of, this is still H2. And then that would be it for this question. So 0.75 times 22.4, this is 16.8 liters of H2. So that's pretty much, part A was just using the molar mass, right? Part A was using the molar mass to go from grams to moles. Part B was using the balanced equation and using our mole to mole ratio. And that was just going from moles of aluminum to moles of H2. Lastly, STP, just really looking at the liters per mole. This is something to definitely note whenever you're asked to find liters and you're doing stoichiometry really with it. Okay, so that's that type of question. Let's see who's next. Okay, Stacy. Okay, let me see what we got. So my homework says, using the Hoffman apparatus for electrolysis, a chemist decomposes 36 grams of water into its gaseous elements. Okay, how many grams of H2 gas should she get? Theoretical, create before, change, and after table. Okay. Let me see what else I can do with this. So first, let's just write out our balanced equation. Because they're telling us that it's decomposition, it's H2O, and this is going to decompose into its gaseous elements, meaning it's going to go to H2 and O2, and then I have to balance this out. So balancing this, we need to just put a 2 here in front of that H2O. Now we have 4 H's, so here I'm going to put a 2 there, and it's balanced. Okay, so this was in its liquid state. These are gases and gases. Now, let me see what else this wants. How many grams of H2 gas? This is more stoichiometry. So we're going from 36 grams of H2O, and should she get theoretical yield? How many grams of H2 gas should she get theoretical yield? Create a BCA. You actually don't have to do a before, change, and after table. What you can do is just convert. So this is 36 grams of H2O. And if I'm just trying to find the grams of H2 gas, then I'm really going from grams of H2O to then moles of H2O. So stoichiometry. And then to moles of what we're looking for, so H2. And lastly, the answer wants it in grams, so we'd go to grams of H2. So that's the process, and that's actually what I'm going to do now. So I'll find the molar mass of water, and we'll do that separately. So H2O, the molar mass of water. So hydrogen is 1.01. I'll multiply that by 2. So this is 2.02. Oxygen is 16. Adding the 16 plus that 2.02 would have been 18.02. Okay, so that's the molar mass that I'm going to use. I'll put the grams on the bottom so that what we just found, that number always goes with the grams, and it's always 1 mole for molar mass. So that's of water. And then now I'm going to do a mole to mole ratio to change the compound. So then I'll put the moles on the bottom, moles on top. So H2O is on the bottom, H2 is where we want to go to. So then now I'll look at the balanced equation, the numbers in front. So then we're going to have 2 moles of H2O per every 2 moles of H2, so 2 to 2. And lastly, we need the molar mass of H2, which is really this part. It's that 2.02 grams of H2, and then 1 mole on the bottom of H2. Okay, let's multiply this all out, and that would have been our answer. So 36 times 2.02 divided by 18.02. And then this is 4.04. And then I'm actually going to leave it as just 4.0 grams of H2, since initially they just gave us 2 sig figs. Yeah. So that would have been the answer for that one. Okay. Let's see what we have now. Bria says, can you do a half reaction problem? Sure. So a half reaction problem goes back to oxidation, reduction, and redox reactions, really. So let me pull up an example of a redox reaction question. And we'll go from there. So let's see. I think I had one earlier. I did actually. Let me see if there's another one that I can use. I'll use the same one since I have it up. Yeah, since I have it up. So, and actually better yet, I have another one. Here we go. H plus aqueous plus magnesium solid going to H2 gas and magnesium 2 plus aqueous. Okay. All right, so with writing half reactions, what we're really looking for is we're going to start off with just our oxidation numbers. Okay, that's always going to be the case with redox reactions, is figuring out our oxidation numbers. So let's start there, and I'll start off with H plus. Anytime we're given a charge, that is just your oxidation number. Once again, that's only going to be the case if it's just one element. If it was a compound and it gives you a charge, it would be different. So we would have to figure out each individual element's oxidation number. But in this case, it's just +1. For anything that's by itself, so it's one element in its solid state, or really just one element, that's going to have an oxidation number of 0. And then next, for H2, this is the same thing. It's now diatomic, so whenever we have a diatomic atom, that's going to have an oxidation number of also 0. And then once again, we have a charge, one element with a charge, the oxidation number is its charge. Okay. What we're looking for now is a change in oxidation numbers, and we're going to look from left to right, or really reactants to products. If we were looking at, let's say, hydrogen, this goes from +1 to 0. That became more negative, or really reduced. So that is reduction. Anytime our oxidation numbers are reducing, it's reduction, because that's actually gaining electrons since electrons are negatively charged. So I like to think of this reduction is reduced, so it's more negative. Now it's different for the other part of this. Magnesium goes from 0 to +2. That's increasing, so that's actually going to be oxidation. Anytime our oxidation numbers are becoming more positive, that will be oxidation, because they're actually losing electrons, since once again, electrons are negatively charged. To write the half reactions, I'll put oxidation first, okay? And then what I'm going to do is I'm only going to place the elements or compounds or whatever we have that's only involved in oxidation. I don't care about reduction for this first part. So what I'll do is I'll just put magnesium in its solid, and then going to magnesium as an aqueous or an ion in its aqueous state. And then next, I'm going to do the same thing for reduction, everything that's just involved in reduction. So for reduction, only thing involved is the hydrogen. And then from there, we have to state how many electrons we have, okay? So now what I'm going to do is I'm going to figure out how many electrons do we have overall. For oxidation, I'll start off with the 2. Okay, so I like to think of it as like products minus reactants, and I'm looking at the oxidation numbers. I'm subtracting those two. So 2 minus 0 would give us 2 electrons. For oxidation, you have to add to the product side. So I'm going to add 2 electrons on the product side. That's always for oxidation. For reduction, add to the reactants. So reactants, reduction. Okay, add electrons to your reactants for reduction. Let's figure out how many electrons to add for reduction. So I'm going to go from 0, and then I'm going to subtract that by 1, and that gives us really 1 electron. We don't care that it's negative. Electrons are negatively charged regardless. So I'm going to add 1 electron on the reactant side, and that's how you would write your half reactions. Okay, hope that makes some more sense. I'm going to move on to another question. Raja says, what number of sig figs do you use for your final answer, and when do you round? So so for that, it depends on what you're given. So let's state if here, it depends on what you're given. It also depends on what operation you're doing, meaning if you're multiplying, dividing, adding, subtracting, and so on. So like, let's say if a question were to be like 43.7 grams and change that of, let's actually state that this is of oxygen, okay? And we have to convert to moles. Sure, why not? So if we had something like that, the only value that they gave us initially, and that's going to be involved in multiplication, right? This would be multiplication from going from grams to moles, or actually division. There we go. Since we were only given 3 sig figs initially, then your final answer would round to just 3 sig figs. So that's something to kind of note whenever you're multiplying. You always want to round to the least amount of sig figs, and that's specifically with the values that you were like given. So like this 16, I placed that there. I wasn't given that amount. So that's why I only look at, oh, there's going to be 3 sig figs. Okay, when I actually figure this problem out. Now, if I were adding or subtracting, like let's say if this were 37.1 plus 6.87, okay? When you're adding or subtracting numbers, then you round to the least amount of decimal places. So with decimal places, there's only 1 decimal place here. There are 2 decimal places here. So you would just round to 1 decimal place after you actually do the operation, after you add or subtract. So that's the main thing, that's how you would know when to round. Okay. Let's see who's next. MJCS says, write the combined equation, please. For what? So I don't know if you're still typing your question. I'm probably, but let me know what combined equation. All right, so let's go back to another question while they add theirs. I'm going to go back to another question from Jazzy. So she states a 200, I'm just looking for it, 200 milliliter saturated solution of potassium nitrate is made is made 90 concentration. If 15% of our solvent evaporates as the solution is slowly cooled. Oh, I see. Celsius. 90 degrees. And then is slowly cooled to 30 degrees Celsius. What mass of precipitate is produced? So if we have 200 milliliters of our solution, okay. So then they're giving us 15% of our solvent evaporates as the solution is slowly cooled to that. What mass of our precipitate is then produced? Okay. I would just look first at like grams of solute that has to be on top, and then our grams of our solution would be on bottom. I'm still looking at that mass percent sort of like formula, and then times 100. So what they're giving us is they're at least giving us the amount of solution. It's milliliters. And then they don't give me density, which I'll see what I can do with that. But 200 milliliters of saturated solution of potassium nitrate is made at 90 degrees Celsius. If 15% of our solvent evaporates as the solution is slowly cooled to 30, what mass? And I think we're still looking at solubility tables, right? I think that's the case because we would have to be given something else. You know, I think I closed that. But yeah, I think we're looking at solubility tables. Let me go back to solubility tables or curves and see what I can find with that. Okay. Because we would have to look at the temperatures, and I believe that they give you that. So if I'm looking at 90 degrees Celsius, that's at 200 milliliters. And then if I'm looking at 30 degrees Celsius. Okay. So at 90, it's here. This is temperature. And then 30, let's say it would have been like here. This is 0. And if I'll state this is 20, 40, 60, and 80. Okay. So I'm not sure what yours looks like. I'm just going to draw kind of one that I'm looking at. This is specifically for potassium nitrate, so we'll see where we go with this. But this would have been 200 milliliters of saturated solution, and then if 15% of the solvent evaporates as the solution is slowly cooled. So I started off at, let's say here, right, we started off at 90 degrees Celsius. So, and that's at 200 mils of our solution, and it's saturated. That means that there's more solute in our solution. So I most likely would have a higher point on my graph. So if something is saturated, that means that there's more solute in the solution. And if it's super saturated, then that means there's even more solute in your solution. If it's not saturated, then you don't have too much solute in the solution. Okay, I think you get where I'm going with this. But since this says it's a saturated solution, I'm going to put this a tiny bit lower, but this would have been roughly, actually, no, that was fine. It's roughly like 80. And then, like I said, you would have to look at a table for this. If it says if 15% of our solvent evaporates as the solution is slowly cooled, okay, then I would think of it this way. The fact that your solution is equal to your solute plus the solvent, and if 15% of that solvent evaporates, then our solution is then decreasing, and that pretty much would look like either like this or actually like that, and then possibly could have been at 30. I actually would have had to have seen the table that they provided, which I'm pretty sure possibly they did. Yeah, so I don't know if they did provide you with that, Jazzy, but you would have to look at the table and understanding how to use that table, just going from the temperature where you started with the 90 degrees Celsius and then stopping at that 30 degrees Celsius. Like, let's say if this was 45, then that's how much was left over. That would have been the grams of it. Okay, so that's what I would assume they gave you. Okay, so now I'm going to go back to, I think we got more information from MJCS. Half equations, okay. Oh, right, the combined equation. Got it, like combining, like balancing the electrons. Okay, let me go back to that question. And let me see what I had before. Let me go back to that question. I think I had it somewhere. Yeah, I did. Okay. And I'll rewrite those half reactions that we did before, and then we'll balance this out here. Okay, just going back to this question, we really found our half reactions before. This is H2 gas, magnesium 2+. Okay. All right, so before we found that our oxidation part of this, and I can re-put the oxidation numbers, this was +1, 0, 0, and +2, where we stated that this was reduction, right? And then this was oxidation, okay? So in oxidation, we said that we had 2 electrons that were moving, and then we had 1 electron here in reduction. So redrawing this out, the half reactions, we had, where was it? Mg solid goes to an ion. Okay, and then we added 2 electrons on the product side for oxidation. You always do that. And then for reduction, we had H+ aqueous, and this goes to H2 gas. And then we'll add 1 electron on the reactant side, since that's always the case for reduction. Now, with balancing this out, you always want to have the exact same electrons. So what I would do is I want to multiply 2 by this entire half reaction of reduction. So every single coefficient in front will get distributed or be multiplied by 2. So really this is now 2 electrons plus 2 H+. Okay, and actually even before doing that, guys, one little thing. We need to have this balanced. So this actually isn't balanced. Before I even do that to the electrons, we have to make sure that these hydrogens are completely balanced. I'm going to place a 2 here, just stating that those are now balanced, making sure our magnesium is balanced. It is, so now it's fine. Now I can distribute that 2 in. That would have changed everything and would have been wrong. So now I'll distribute that 2. So always making sure everything's balanced. And then this would have been 2 electrons plus 4 H pluses. Okay, and then this is 2 H2's gas. And then from here, we're going to add all of our reactants together, okay? And then we'll also add all of our products together. So something that will happen is our electrons will cancel. They always will cancel since you have to balance them and make them the same. And then our final answer, and I've typically been asked this question, does the order matter of the reactants or the products? It does not. Since you're adding everything up, doesn't really matter. It really doesn't. Instead, what matters is just everything is on the correct side, right? So as long as it's a reactant, doesn't matter the order, or product, same thing. So this would have been our answer. This would have been the entire balanced redox reaction under neutral conditions. Okay, let's see what else we have. Okay, and April says, I'm having difficulty understanding the difference between a strong electrolyte, a weak electrolyte, and a non-electrolyte. Can you help me understand how to identify each type? Yes. Okay. So let's start off with a strong electrolyte and what's really going to happen. So if an electrolyte is strong, that means it completely dissociates. Okay. So that's something to note. If it's strong, it completely dissociates in water, or just kind of like think of it as dissociation is really dissolving or breaking apart into ions. Okay, so this is going to dissolve, or I'm going to say dissociate completely. And what's going to do that is anything that is ionic. So that can be something like a salt. That can be something like an acid. Okay, specifically a strong acid. So I could have stated, let's say NaCl. Because this is ionic, this is a plus, this is a minus, that will completely dissociate, thus that will be a strong electrolyte. Same thing with a strong acid like HCl or HI or HBr. Okay, any of those or any sort of strong acid would be considered a strong electrolyte. Now with a weak electrolyte, that's going to partially, I'm just going to say weak. Weak electrolyte, that partially dissolves, so it doesn't completely dissociate. So I'm going to say partially dissociates. So that can be anything like, let's say a weak acid. Okay, what else? Something that would have been a little bit harder to break apart. So a weak acid would have been something like H3PO4 or HF. I know there's like a list of different types. Maybe they provided you that, or it might be in your book, but that's something to kind of look at, is that strong is going to completely dissociate, weak is going to partially dissociate, non is not going to dissociate whatsoever. Okay, so no dissociation. That is the main concept with this. So no dissociation is understanding how will everything break apart. So if something were to be some sort of, like, let's say a hydrocarbon, and actually, yeah, something like a hydrocarbon, and that would look like, by the way, a hydrocarbon is this. It just consists of carbon and hydrogen. Let's say it's this big old long thing like CH3, CH2, CH2, and it just keeps going. Okay, CH2, CH3, and so on. So something like that, or even something a little bit smaller, that would be characterized as a non-electrolyte because it will not dissociate whatsoever. It's not going to break apart into ions because there aren't any ions to break apart into, really. Okay, so that's something to kind of look at. That's the main concept. Hope that makes some more sense, April. Who's next? Okay. And what's the formula for silver? I think someone already answered that, and that is correct. Ag. Cool. Yeah, so Ag is silver. Let's see. Let's go back. Anybody else? Maybe towards the beginning. So sure. So I'm going to go back to another question from Angie. Okay, since there aren't any new questions, I'm going to go back to you guys. So Angie, I'm going to answer another one of your questions, and it's how to draw 3-ethyl 2,3-dimethyl pentane. Okay. So this is a little bit of, this is the beginning of OChem or the end of General Chemistry 2. This is where you learn some OChem. So what I'm going to do first is just draw the entire amount of carbons that we have. Pent means 5. So this tells us there are 5 carbons. So doing that trick again, there's 1, 2, 3, and 4. I think 4, and I actually draw out 5. Okay, so now what I'm going to do next, because that's correct, there's 5 different carbons. I'm going to number this all out. We have 5. Now let's place all of our substituents. So ethyl means that there are 2 carbons, and that's at 3. So I'll put 1 and 2. So this is going to be the 1 and the 2 carbons. Next, for dimethyl, this tells us that there are 2 methyl groups at the location of 2 and 3. So methyl is just 1 carbon, so I'll put really just a line and then a line also at 3, and that's it. That's all. That's how we kind of look at it. I like to start at the end and always start at the end. You look at pentane, since that's 5 different carbons, draw the carbon chain first, and then all of those numbers tell you the location after you've numbered the carbon chain. Then that tells you the location where those substituents should go. And then quick little thing just to know is that definitely know these substituents. Methyl is just 1 carbon. Ethyl is 2. Propyl is 3. So propyl. And then butyl is 4. Okay, so those are going to be very, very helpful. Definitely know those. Okay. Let's see. The biggest anime lover. Okay. What is the difference between atoms and elements? Okay. So let's say if we were to look at, let me see what I can kind of go into. So an element we know is pretty much just found on our periodic table. Okay. Atoms tend to be composed of everything. So it's not that they're different, I would say, since everything is composed of matter and everything's really kind of composed of, therefore, atoms. I wouldn't really see that there is much of a difference. However, it would have been, yeah, interesting question, but Na would have been an element, right? However, we could have also been asked, find how many atoms, like let's say HCl, sure. How many atoms make up this acid? Okay. Then from there, you're just looking at, oh, well, there's 1 atom here, hydrogen, and there's 1 atom here, chlorine. There are 2 atoms. So in chemistry, you tend to kind of use those interchangeably sometimes. When asked a question like this would have been called an element. However, sometimes they'll ask how many atoms are within this compound, within this, molecule or whatever they give you, and you have to kind of take out every single type of atom. So I wouldn't really say that there's much of a difference. It's just understanding what the question is asking. But yeah, I wouldn't say there's much of a difference. Then let's see another question. GI says, why isn't it 3-propyl methyl? Oh, here. Let me refresh this. So, like all together, and then that's it. Yeah. When when you're doing this, you have to know the ending. And it goes back to here. Let me re-explain this. So let's say alkane, alkene, alkyne, and that's as much as I'll do for right now. In OChem and with naming, a lot of times there are so many different structures actually that to help us understand, like, this is kind of like a secret code that chemists talk to each other with, but for chemists to understand what type of structure it is and how to draw the structure, what to use, and what's happening, we have to actually state the endings, okay? So like, let's say for alkane or the ane, that's why you saw that, oh, it ended in pentane, or it would have ended in methane. That tells us that that's the carbon chain. And then ane refers to there only being single bonds. Like, let's say if I were to have done that question that you stated. So 3 propyl, and it should have been methane. Then I would have drawn methane, and then actually I wouldn't be able to even do that per se, but yeah, actually that wouldn't have worked. I'll tell you why though. If I were to attempt to draw this, methane is just 1 carbon. So that would have not even, like, I couldn't even have just drawn a line, okay? So like this already consists of 2 carbons. So that's not possible. So methane, like, there aren't 3 carbons to actually be able to state that that was methane. If I were to try to do like, oh, propyl I know is 3, and then at, like, I can't even state the location at 3. So that's why it doesn't work. You have to have the longest carbon chain at the end. So this always has to be the longest carbon chain, okay? So instead, maybe we could have done that this was 3 methyl propane. Now it'll work because I have to always start off with drawing the longest carbon chain, which propane means there are 3 carbons. So that's 1, 2, 3 technically. This is 1, 2, 3. Now I can actually state the location of our methyl group, which would have been here. Okay, so that's something too. I know this technically wouldn't work either, but that's like the main concept with it, is that you always want to have the longest carbon chain. Like when you're numbering and you're naming in general, that's why that doesn't work. The 3 propyl methyl, since you only have 1 carbon and you can't even state the location of that propyl at 3. Okay, hope that makes more sense. And then let's see. Jennifer Rosas says, just finished my chem exam 2 days ago. Thank goodness. Thank goodness. I'm glad you're done. Yay, summer. Congratulations. I hope it went well. I hope everything, once you get your grade, let me know. But yeah, congratulations for being done. What an awesome feeling. I remember it. Awesome, guys. Let's see what else I could answer. April, you just stated another question. Are all compounds with polyatomic ions considered weak acids since they partially dissociate? Not all of them. So there's actually a list. There's a list of strong acids, and you can honestly even just type it in Google and it'll show you the different list of common strong acids and weak acids. So there's a lot more to it rather than just the structure itself. It has to do with how the elements are reacting, how they react with other things. So that list is something to just kind of know. However, I believe there is one, I think it was HNO3, that was a strong acid. Here, I can pull up the strong acid list to know. But yeah, those are definitely, yeah, it is. So like HNO3, though this is a polyatomic ion, it's still characterized as a strong acid. So I wouldn't say to, just to know that. Yeah, that's kind of something to state. And then same thing goes for, like, let's say if you had HClO4, HClO3, all of these are strong. All of these are strong acids, thus they will completely dissociate. Thus, they are strong electrolytes. Okay, so that's something to know. And then G just said, oh, okay, thanks. Just started organic chemistry at college, and it's so confusing. I remember OChem, really, I do. The fact that they don't always tell you like what every little symbol, it's a new language. Let's just say it at that. But I think the best thing is just like, that's why, when explaining it, I like to kind of pinpoint what are the things that are changing, what does every little symbol, every little like sharp turn actually mean, right? So knowing that information is very helpful. But I would just say for OChem, keep studying, keep like seeing all the different patterns. That's personally what helped me do well in OChem. And just, I literally studied every single day since it was a challenging class. Okay. And then MJCS said, I got an A in my A-level mocks 2 weeks ago, but word got out some people cheated. Oh my gosh. And now I have to revise again for another set of mocks next week, and I'm stressing so badly. Wow, I'm sorry that even happened. That whoever cheated, or the people that cheated, ruined it for everybody. But the fact that you got an A the first time means you can do it again. Okay, so keep studying. Do what you did. Clearly, you did something right to get an A. Okay, so keep working on it, and I will be having, more Q&As as well. I have another question from Jackie, and she says, can you please do a limiting reactant question when only given moles of an element? For example, if we have CH4 plus 2O2, CO2, and 2H2O. Okay, and we were given 0.250 moles of methane. Methane is CH4. And where'd it go? There we go. And then was burned in 1.25 moles of oxygen or O2. All right, so figuring out the limiting reactant for this, since they don't tell you what product they want you to actually solve for, it doesn't matter what product to go to. So what I would have done is, let's go from moles of, I'm going to say each reactant, okay, we're going to do this twice, of each reactant to then the grams of our product. And like I stated, it doesn't matter which product you decide to use. So I'm going to use CO2. Why not? Or if you used H2O, it would have given you the same limiting reactant. Doesn't matter which one you choose, since they don't specify what product they want you to go to. So let's start off with the moles of our reactant, our methane, CH4. And then what I'm going to do is I'm going to go from moles of CH4, and then I'm going to go to moles of our product of CO2, and then lastly get to grams of CO2. Okay, so then all I have to do is multiply by a mole to mole ratio, so moles of CH4 on the bottom and moles to what we want, CO2 on top. Going back to our balanced equation that was provided, there's only 1 mole of CH4 per 1 mole of CO2, so that's a 1-to-1 relationship. I'll place that here, 1-to-1, and I'll multiply that by the molar mass of CO2, which carbon would have been 12.02, and then, or 1, and then oxygen would have been 16 times 2, or 32. Add those two together, and that gives us 44.01, and I'll put that on top, 44.01 grams of CO2 per every 1 mole, and then we'll multiply and see what that gives us. 0.25 times 44.01, that gives us 11.0 grams of CO2. I'm going to do the exact same thing with the other reactant. So we have 1.25 moles of O2. Once again, multiplying that by our mole-to-mole ratio, putting the O2, moles of O2 on the bottom and moles of CO2 on top. And we find those values by using our balanced equation. So our balanced equation here, we have 2 moles of O2 per every 1 mole of O2. So we'll put that here. So 2 moles of O2 per every 1 mole of CO2, multiply by that exact same molar mass that we found before. And then we'll compare those values and find what produced the least amount of CO2, which is our product. So 1.25 times 44.01 divided by 2. This gives us 27.5 grams of CO2. So CH4 produced 11 grams of carbon dioxide and O2 produced 27.5. So we know CH4, the methane, is our limiting reactant, and then therefore our O2 is our excess. The only difference, like typically I know they give you grams of reactant and then grams to product. It saves you a step from starting at moles, okay? So you don't have to find the molar mass of like the first reactant and then go from there and go from grams to moles and so on. Instead, it saves you a step and it's actually shorter, so that's nice. But yeah, that would be the answer for this one. Hope that makes more sense, Jackie. All right, maybe one more question. Pamela, you asked, can you explain how to solve problems about weak acids? What about them? So like, what would the question ask you? What would it state? Let me know. Because it's a little bit too general. And I can be here for a while talking about it, okay? But yeah, let me know what type of question that would be, what's confusing you. Next, Candace says, can you talk about reactions of organic molecules, like substitution, addition, and elimination reactions of organic compounds? This is from pre-AP Chem in grade 11. Thank you. Wow, you guys actually talk about that stuff already. I'm shocked. Yeah, I can give you a few things that actually occur. Let me find some examples real quick with those types of OChem questions. Here we go. Okay. And then Candace, I'm curious, since you guys are learning that so early on, where are you actually learning? Like personally, like I'm from California, like where are you from? Like what school district and whatnot? That I'm curious to know where you guys are actually learning OChem. I don't remember learning that or even seeing any of my students learn that in grade 11. Yeah. I mean, it's awesome that you can. Okay, so let's say substitution, and let me see if I can find some. Better yet, I think I have my whole book here. So let me do a general process here. Give me one sec to just look for an example. Yeah. Okay, so I can start off with something like, let's say, substitution. And let's say if I'm going to do like the general process here. Let's say if I had something like this. Canada. Okay, cool. Well, hello from California. Cool. All right. That's honestly pretty awesome that you guys get to understand this stuff already. That's amazing. This is substitution that I'm doing. Okay. So with substitution, what's going to happen is that our leaving group is going to be that halogen attached to the carbon. So this halogen is actually going to leave. So any good leaving group will leave. Good leaving groups are halogens as well as water. So that leaving group is going to leave. And then what's going to happen is the fact that it's stating its substitution is something else is going to take its place. So it's substitution. You're pretty much just swapping, like, let's say the halogen for another halogen, or you're kind of like just switching two different elements for each other. So then our new product would have been that bromine is now attached, okay? And then that's pretty much all that's happening, is that those two are swapping, and then Cl- is still here. But that's kind of like the concept with substitution. You're just switching them out. And then what else? You asked for addition? Yeah. Let's say if we had an alkene. I hope you guys went over that already. An alkene is really just talking about a double bond. Like let's say if we had something like this. Yeah. So if we had something like this, and these are just two different carbons double bonded, that's what an alkene is. And we added H2. Okay, this is an addition reaction. So what would happen, and I'm going to redraw this H2 as how it looks like, what's going to happen is the double bond is going to start the reaction. And that's going to take one of the hydrogens. This bond would then break. And essentially what's happening with an addition reaction is that we're literally just adding on. Okay, so the concept here is that the double bond is going to break. It's no longer going to be an alkene. It's going to be an alkane. Alkane is just a single bonded carbon. Right, single bonded carbon chain, while an alkene has a double bond. So then now this is going to break, and all of those methyl groups are still going to be there. However, we just attached on hydrogens, okay, on the carbons where that double bond broke. That's it. There's no byproduct. All we're doing is adding on. You're breaking that double bond to become a single bond. And then let's see for elimination. Let me see if I have a simpler one, because the majority of my questions are for OChem students. So let's see if I can find one real quick. Just a simple elimination question. Let me see real quick if I can find that. Yeah. Okay. So let's say if I were to have some sort of elimination question, and it sounds like just like the addition kind of said, we're adding something on. Elimination, you're removing something or eliminating something. So like, let's say if we were to have something like, I'm being picky. Let me not be. Okay, let's say this. Sure. Okay, let's say something like this. This is hydrogen and this is bromine. All right, what's essentially going to happen with this reaction is that HBr is going to go away. So both of these are going to basically leave. And in that process, this is going to, and here, let me actually show you what happens. The leaving group leaves, right? We have a leaving group that's going to take off. And then in the process, I don't know if you guys have talked about something called the carbocation. Carbocation is just a carbon with a positive charge. So that's what would happen here with our leaving group detaching or going away. And then what's essentially going to happen is that bromine is going to be attracted to that hydrogen, and that's going to steal that hydrogen. And this bond is then going to be donated to make this a neutral compound. Okay, now it's going to be neutral, and then this is going to donate its electrons, and then now we just formed a double bond. Okay, so this is essentially what we would have built or created, and then our byproduct is just that HBr. Okay, so really the main concept with addition, something adds on, substitution, something like swaps or substitutes for the other, an elimination that completely gets eliminated or removed. That's the concept. I don't expect you guys to be doing anything too crazy with that or getting anything, you know, nothing too bad since it is just the beginning. Okay, guys. So thank you so much for being here. And I do have another Q&A, another 2-hour Q&A tomorrow and the next day and the next day. So I will be doing this for another 3 days. So Friday, the times I have is the same exact time. It's going to be from 4 to 6 Pacific time. So make sure to come back tomorrow if you have any more questions. And then I also will be doing that on Saturday from 10 a.m. to, I believe, 12. And then that's also Pacific time. And then on Sunday, I will be going, I think the time was 11 to 1. Okay, so Pacific time as well. So make sure to check back. I will be doing this again and again for 2 hours. And the reason why I'm doing this is because I promised at 10,000 subs, I would do an 8-hour live tutoring session. And I thought, well, you know, since we hit that mark and I'm so appreciative, I wanted to have a lot of people actually be able to join. And I know not everybody can do a certain day. So to keep my sanity and not do an 8-hour complete session, to actually break it apart into days and have more people, you know, be able to show up. And let's say, if, you know, you go over and study and you still need help with something, oh, there's the Q&A for the next day. So yeah, and I hope this helps you guys so much for your finals and your exams. And I'm already seeing so many kind words. Candace says, thank you so much. That really helped. Have a great day. Thank you, you too, Candace. And April says, awesome. Thanks again for your help, Melissa. Have a wonderful day. You guys are so kind, so sweet. I'm happy to do this. And I hope to see you guys tomorrow. Have an awesome day. See you guys.